Alright guys, so today we're going to be doing chemical equilibrium. I know that Arham spoke about the different types of intermolecular forces and intramolecular forces in the last video, so this is kind of a continuation of that. So let's get right into it. What is equilibrium? So equilibrium in chemistry is where there's no net there's no net difference in concentration. So, for example, we have reactants and products. When they are in the equilibrium state, this is very important for you to understand. It's not that there's no movement between them. It's not that there's no more reaction happening, right? And that's why, for example, let me just write like a very simple equation. Gives AB. Okay, this means that it's an equilibrium. Now, this just means, it does not mean that this reaction does not happen once we reach it. It means there's no net difference in concentration. Now, what does that mean? So that means the concentration of reactants and products remain the same. They don't change, but the reaction still takes place, you know? A plus B still goes to AB and AB still decomposes to A plus B, right? So equilibrium is the state at which the concentration of reactants and products stay the same, and there is no net movement. But, there's no observable changes or net concentration changes. Therefore, the reactions still happen, but just at constant concentration. I just really want you to understand that. So I'm going to repeat it one last time. The concentrations of the reactants and products are at equilibrium when they do not change, but that does not mean that there's no reaction taking place. There's still reactions happening, and that's indicated by the equation line like this. Okay, so, yep, talked about this. All right, so, as I said, equilibrium is the concentration of which reactants and products stay consistent. Okay, so to find this equilibrium, the formula is very easy. It's represented by concentration of products over concentration of reactants. Now, in these little diagrams, very, very simply, it's shown how we reach equilibrium by concentration. So each one of these little bubbles, the red bubbles, are for B, and the other ones are for A. Now, here we see that there's only reactants, okay? Can't really tell anything from there. These are the products. Let me change my color. These are the products, right? So here's where this reaction actually takes place. Now, this is the timeline of the experiment happening, the reaction taking place. As we can see, there's more and more products taking place. However, once we reach here, we see that there's no net difference. There's still 5, there's still 3 of the A's, and there's still 3 of the B's. So here, there's no net concentration difference. So we are able to calculate the equilibrium constant. And what is that? In simple terms right now, we're going to get into specific ones. We're going to do products, which is 5C over how many B's are there? 3 times how many A's are there? 3, right? Giving this. As I said, this is the more precise definition. The state reached in a chemical reaction when the concentration of reactants and products remain constant over time. Okay? So, I mentioned this again, but I will mention it more and more and more just because I do not want you guys to get this question wrong. It is a dynamic state. Equilibrium state does not mean that the reaction goes to a complete stop. It's dynamic. It just keeps coming, you know? Just means the forward and reverse reactions are equal, but they still happen, okay? Now, This means the rate of the forward reaction. This is the rate of the reverse reaction, okay? These are going to be some terms that we're going to use in some chemical formulas and stuff like that. This stuff is very self-explanatory and you don't even need to think about it. We're going to get into it. These are some graphs about reaction rate and time. As we see the reaction rate, okay, this is the reverse reaction, forward reaction. As VF over VR equals 1, that means we are at equilibrium, right? Because the concentrations are not changing, and the rate at which the forward and reverse reaction take place are the same, okay? That is where you get this guy, chemical equilibrium. It can be shown like this, okay, for reaction time, or it can be shown with concentration. So concentration does not necessarily need to be like this, like it can also be here. So whenever the concentration of, let's say, this is the products, this is the reactants, it starts to plateau here, okay? That means the concentration isn't changing. That means at this point, this has reached equilibrium and this has as well. So at a point where they both plateau, that is their equilibrium point, okay? And same goes on for the reaction rate that we talked beforehand, okay? Now, I'm going to move a little further down. This is repeating the same thing. Oh, this is something I want to say as well. We can have a concentration versus time graph that looks like this, and we can have one that looks like this, okay? The only thing you're looking for is where it's plateauing, okay, to find the equilibrium point, okay? That's all that is. Yeah, that's that. Now, if, for example, the concentration of the products, okay, is higher, it'll be favored in the direction of the forward reaction. This is the forward reaction, right? And this will be favored in the reverse reaction. Why do we say this? This is because the concentration of the products here is higher, okay? So that means that we will reach more products usually than we do with reactants. And here's the opposite. We will have more products than we do with, reactants compared to products. All right. So this is just characteristics of equilibrium. It's talking about what we're going to be talking about, which is called the ICE table. So initial concentration, change concentration, and we're going to be talking about the equilibrium concentration, so after completion. So this is just talking about molar ratios and concentration, and then how to calculate it. So, as I mentioned, equilibrium is products over reactants raised to their coefficients, okay? That is equilibrium's exact definition. It's written here somewhere, but remember that. So whenever you're thinking about the formula, I'll write it for you right here. K equals let me write it like this. K equals products, okay? If there's multiple, it's multiplied by each other, okay? Raised to their molar coefficient. So if it had in the balance formula like 2 CO2, instead of just CO2, you'd write a 2 up top, okay? And this would be over reactants times other reactants, if there is, times the molar ratio of each, okay? So that's how you find the equilibrium constant. This over here is just an example, right? So someone wrote it out. As we can see, when it's balanced, there's no coefficients. So there's no coefficients here, here, or here. You just simply plug in the concentrations and you get your equilibrium constant, okay? There's no unit for this, it's just a constant. Now, this is, again, another 2 graphs showing you that once these guys plateau, this is their equilibrium constant. Same here. Now, this is the reactant. It's decomposing to the products, okay? As we can see here, the concentration of this is higher than that of this, right? So we can tell that it's more in favor to go reverse from this, right? That's something to note, and same here. So right here, there's a lower concentration of the NO2s, there's a higher concentration of the N2O4, therefore it's more favorable for the reaction to go that way. This is, again, another sample calculation. Pretty much what you're supposed to do here and here is the N2O4 has no exponent, it's not raised to anything, but the 2NO2 is, and that's represented right here. And you plug in these two in this formula, which gives you the equilibrium constant. Now, the conclusion of this, stoichiometric coefficients are very, very important. If you're new to balancing chemical equations, do a lot of practice, because you really need to know it well in order to get the right answer. You don't want to be making silly mistakes like that. Now we're going to get into temperature and Le Chatelier's principle. So I'm going a little further ahead, but it's all going to make sense better now. So Le Chatelier's principle, he's a French guy, doesn't really matter what he does, but what he says is, when we have something in equilibrium, right, for example, I'll draw this out for you guys, you have a seesaw, okay, it's at equilibrium, okay? Now, if I were to put more weight here, okay, let's just say that's weight, I don't know what that is, this would then change and look something like this, okay? So, to reach equilibrium here, again, we need to put weight, okay? So, this is true for a couple things. For inputting reactants, products, okay? Second thing is pressure, volume, okay? Temperature. These three things can move the equation around in favor of the reactants or products. So this is just a small example of this. So at different temperatures here, we see that the concentration, so the concentrations will be different. So the equilibrium constant is dependent on temperature. Okay, so at a lower temperature, the equilibrium constant requires only 3 of these guys, but at a higher temperature where they react more freely, you need way more of these guys to be at equilibrium constant. Now this will be for a number of reasons, which we're going to get into. So this is, I mentioned this, but I'm going to go over it again. If you don't know this guy, just understand the definition of the equilibrium constant, okay? Almost everything in chemistry is products over reactants. Just add the molar coefficients to them. Remember it like that. So the equilibrium constant, the product of the concentration of reaction products raised to the power of their corresponding stoichiometric coefficient over the product of the concentration of reactants raised to the power of their corresponding stoichiometric coefficients at a given pressure and temperature. Remember that. So, stoichiometric coefficient, when you balance the chemical equation, goes here. This is for products. This is reactants. Okay? And if there's multiple, you multiply them together. Okay? Remember those. So, now the different types of equilibrium constants, I'm going to get into in a second. We have Kc, Kp, Ksp, Kw, stuff like that. Right now, we're just going to get into Kc and Kp. Okay, later on, we're going to move on to other things. Kc is based on concentration. C, concentration. Okay, calculated in the same exact way. Okay, now Kp is also calculated in the same way. Okay, right? These look very similar, and it's for pressure. Okay, something I should note very quickly is Dalton's partial pressure law. That means over here, P1, P2, whatever, all the partial pressures give P total. Okay, now this is the ideal gas law. Okay, we don't really care about this right now, but what it helps us know is this guy. We derive this equation from it. So if they give you the equilibrium constant for concentration, R is a constant, Rydberg constant. I think it's 0.8026. Okay. Temperature, they'll give it to you. What's N? N is the difference in number of moles. So these all represent moles, right? Here, the coefficients. What you do here is the moles of the products minus the moles of the reactants. So if this was 2, 1, 2, 3, this would be 5, this would be 3, 3 minus 5 would be negative 2. The difference would be 2, okay? So you don't say negative. A difference can never be negative, okay? So, that is placed here, and then you calculate it like that given the Kc, or you can work backwards, okay? This is just an example at higher altitudes. I'm not going to explain this. It's just an example, a real life example, not really important. They're not going to ask you about it. This is the example I gave about the seesaw, same thing, but just with blood pH. This is the Chatelier's principle. So in minimal terms, it says if a system at equilibrium is subjected to a stress, the system will react in a way to relieve the stress, right? The seesaw. More weight, you have to put more weight here to balance it out, okay? And as I said, this happens with concentration of reactants and products, pressure, temperature. Pressure / volume, okay? Because if you make the volume smaller, pressure goes up. They go hand in hand, right? So, changes in concentration. I know there's so much written here. I'm going to tell you guys how I think of it, okay? Because no one wants to sit here and watch me talk for 2 hours, right? Changes in concentration. If the concentration of the reactants goes up, we go to the right. Why is this? This is a seesaw. Actually, let me this is a seesaw. Okay, right now we're fully balanced. Let's say we add 2 of these now. It will look like this, right? So to balance it, we have to go to the right to put weight here to then finally end up at equilibrium again. Okay, so whichever side you're adding to, you go the opposite. We know in a chemical equation, reactants are on the left. I don't know if it's backwards for you guys if you're looking at me, but we know reactants are on the left, products are on the right. If we add reactants, we go to the right to add more weight you can think of. If we add products, we go to the left. Now they might try to trick you. They might be like, what if we remove products? Okay, then we go the same direction. If it's add, opposite direction, remove, same direction. Now, let me skip pressure, okay, for now, and we're going to talk about temperature. Temperature. So, I'm going to use this little bit of space. So we're going to do A plus B is an equilibrium, gives C plus D, okay? Now, I'm going to give you guys 2 examples. Let's say this has a delta H of 34, okay, joules, whatever. Delta H is heat, okay? When it is positive, okay, that means it's taking the heat. It's absorbing the heat. So the heat comes on the reactant side. So remember, if it is negative, if heat is negative, right? Let's say I'm heat, okay? If I'm negative, I'm losing something, right? I'm losing heat. If I'm positive, I'm gaining heat, okay? So if I have positive money, I'm gaining money. If I have negative money, I'm in debt, I'm losing money. Very easy to think of. Now, this is so important. Sometimes the delta H will not be given to you, but common sense. When we're going liquid to gas, what happens? You have to heat up the liquid. Okay? Now, heating up the liquid means what? Does it mean it's losing energy or gaining energy? Think of it in particles. This is a liquid. This is all its particles. Okay, it's moving a little bit, maybe this much. This is gas. They move like this. They're super, super high energy, okay? So, it's a endothermic process. Endothermic gains energy itself, right? Exothermic, it releases energy. Now, why is this important? Why did I have to talk about all that? Very simple. I'm going to write another equation real quick just to make sure you guys understand. Okay, so what is this? Endothermic or exothermic? Give you 1 second to answer. Boom, endothermic. Good job. Now, what's this? Sorry. Exothermic. Good. Exothermic. Don't take spelling lessons from me. I'm not the best at it. But, so, we know these two, right? Now, since it's endothermic, okay, let's imagine the heat was not here. You had to figure it out. Since it's endothermic, it'll be on the reactant side. So, you figured it out. If it's exothermic, it's on the product side. So you put it in the equation, visualize it for yourself. Okay? This is how I go through things, and I think it's really beneficial. You'll get a better mark. If you see it on paper, you won't like... Sometimes, you think, you're like, okay, so if it's endothermic, what is it? Is it releasing it? No. If it's endothermic, endo gains itself, exo, exit. Leaves energy, one's negative, one's positive. Leaving, negative, positive. I know I'm saying this a bunch of times. I really want you guys to know it. Okay? So, now think of heat as a reactant. Don't even think of it as heat anymore. It's a reactant. Imagine this is F. Okay? F. Same thing we said. If you increase the concentration of a reactant or product, it goes to the other way. If you remove it, it goes to the same way. Okay? So, what happens? F, which is heat, for an endothermic reaction, if we were to increase the heat, okay, for this type of reaction, we need to compensate by shifting to the right. Because there's higher heat, And the same goes if we remove it. We go back. We go to the left, okay? And the exact vice versa goes for exothermic reactions. So I want to show you guys, there you go. So if you raise the temperature here, remember F, that's heat, for example. It's endothermic, okay? Boom, it favors an endothermic reaction. What does that mean? A shift to the right. Very, very simple stuff. Again, if it's exothermic, negative H value. If it's endothermic, positive H value. Okay, it's supposed to erase, but didn't. Okay, now we're going to talk about pressure, right? And then, yeah, so this we talked about as well. Pressure. So, changes in pressure. Pressure, imagine you have a balloon. I don't know how to draw a balloon, but imagine this is a balloon. You have your particles, right? You have your 6 particles. Then you make it super small. You decrease the volume. Then the 6 have to be so close together, okay? So, if the pressure increases, okay, then to relieve the stress, we need to have a shift. The Chatelier's principle, right? But this one doesn't really work in terms of thinking about it in terms of concentration or the heat, The trick is even simpler for this. So, I give you an equation, A2 plus B gives AB Okay, now this is not balanced, right? A2, we need 2 A's, now we have 2 B's, okay? I'm going to draw this in red. Tell me the molar coefficients of A. 1. Good. What is it for B? 2. Good. What is it for AB? 2. What did we say this represented? Difference in N. Moles of products in terms of molar coefficients minus moles of reactants. So we do 2 minus 2 plus 1, 3. So this would equal -1, which is just 1 because it's a difference. But which side has more? If we had to put this on a seesaw, numbers. We have 2 here, we have 3 here. This does not work. It's not balanced. 3 weighs more than 2, right? So it looks like this. Okay? Just to visualize it for yourself. Now, that's the same way pressure works. Okay? So, you guys could just look at me for just a second. I don't know how to explain this very well, but... Okay. This is my hand. Okay? This, imagine there's a balloon in here. There's a bunch of different particles in here. Let's actually just imagine 2. Okay? The side that has the more number of moles, for example here, okay, there's 2 compared to the 1 potassium chloride, or pentachloride, there's more particles. So when you squeeze this together, you increase the pressure, okay, and you decrease the volume. Remember, increase pressure, decrease volume. Decrease pressure, increase volume. Okay, so vice versa. Get that in. As you increase pressure and decrease volume, there's more of the particle with the higher number of moles, right? The reactant side of this example over here has more particles. So that means that it's going to be closer together, higher repulsion. Imagine, the more number of particles of one thing, same thing of concentrations. You have to move to the other way. So, since here we have 2 moles compared to 1 mole, as you get this increase in pressure, we're going to have to do a shift to the right because there's already a lot of particles here. So we have to compensate. That means we're adding reactants. Think of it as you're adding reactants here because of the number of moles. That's pretty much it. That's the Chatelier's principle. I hope you guys got it. Let's move on. Yep. This is just, again, showing you where equilibrium is achieved. And if you were to add something, then how does that compensate with it? Good. Okay. Now, these are changes in reactants or product. This is how you visualize all of this. It's so simple. I know these graphs always, when I look at them the first time, I get super scared. I'm like, I have no idea what's going on. Why is there a jump here? Why does this look like that? Why does this look like that? You know, it's weird. Okay, so this is initial equilibrium. This is that other graph we talked about where it's just like this, and they plateau, and this is their equilibrium. Okay, that's this constant value over here. Okay, very nice. Now, before I say anything, we're saying there's H2 added at this time. That's the only one that has a sharp jump here, right? That's actually being added. It's not accounting for a shift. It's just being added, okay? That line. Where's H2? Oh, right here. Okay, so we talked about if you were to increase reactants, where does that go? A shift to the products, right? Boom. So, a shift to the product. That means this is the product, okay? Right? This guy. It has to go up. This is the increase to compensate for this, okay? And then the other one, the N2, has to compensate as well because it's a reactant, so it goes down a bit. That is the whole visual of what we call Le Chatelier's principle. Very simple stuff. Okay? This is the same thing I talked about for temperature and also for pressure. I think this just confuses you a little bit, and they won't ask you to ever draw this or look at this. Just remember, in terms of balloon number of particles, the one that has the higher one, you shift to the opposite, right? Yep. That's just whatever. Okay, this is important. What is a catalyst? Okay, we have this in enzyme, stuff like that. It's for activation energy. Let's say some reactions don't just happen without any energy. They require an input of energy, and that's represented by this EA, activation energy. So the reactants need some type of energy to reach this point at which they can start their reaction to give you the products. Okay, follow me till now. So this activation energy can actually be brought down by something called a catalyst. Imagine a catalyst is, let's say, the friend of the reactant and product, and makes them have an easier time meeting each other. Okay? Imagine it's a phone that you're texting someone. You'd have to use a carrier pigeon before, now you use a phone. Just, I don't know. Remember funny things so that you remember it on a test. Now, if they ever say, how can you decrease activation energy? Remember, that is done by a catalyst. Okay? Okay, so what does the equilibrium constant mean if it's above 1, 1, or under 1? That means if it's above 1, remember it was products over reactants, okay? Remember that. So if we have more products than reactants, okay, the equilibrium lies to the right in favor of the forward reaction, right? Because we're going left to right. And the opposite goes from right to left. And if it's just 1, then it's in favor of both. They happen at equal rates. Done deal. Okay, very simple. Think of it as math. Again, I really want you guys, whenever you're confused, think of a seesaw. This little thing. Okay? It helps so much to visualize and see how this works. Right? Because if you add a lot of concentration for the reactants, you need to add this guy weight so that he can come down. Right? Okay, this is the same thing as equilibrium constant. Okay, same way, it's calculated the same exact way, all that kind of stuff. But it's called the reaction quotient. What does it do? It lets us predict which direction is this reaction going in. Is it going in the forward direction? Is it going in the reverse reaction, right? So it is the K value at equilibrium. Okay, now this is done through molarities. Molarities, another word for this guy is concentration, right? Because molarity is mole over liter. And that's represented by M, which is molarities. Okay, so this is where you compare Q and K together. So K is your equilibrium value, okay? Now, Q. If Q is smaller than K, okay? So, very simply, K is the actual equilibrium constant. Q, you calculate it the same way, but it's with the concentration they give you at that moment. You know what I mean? It's not exactly at equilibrium. You don't know if it's at equilibrium, but you compare it, right, to find it. So, if Q is smaller than K, that means like this. You have not enough reactants as products, therefore, we go towards the right. When Q and K are equal to 1 to 1, they're perfectly at equilibrium. And if reactants are more than products, then we need to compensate by going to the reverse. Okay, so must occur. Why is that? Products are consumed, reactants are formed, right? So the numerator of the equilibrium constant expression decreases and Q decreases until it equals K, right? So I hope you guys understand that. So pretty much, again, just to say it again, if the products, okay, products are higher than QC for the reactants, okay, that means that we have to go to the products, right? Something that might mess you guys up when you're looking at this diagram is don't look at these. These are like the answer to the questions, okay? Imagine this is just the Q value, this is the K value, this is Q value, this is K value, this is Q value, this is K value. I want you to not look at these, okay? I'm gonna hold my pen here so you guys can't see it, okay? As practice, tell yourself, if they were to give me this as a bar graph, I don't know, the two bars showing me that Q is smaller than K, what does that mean? How does it get to equilibrium? Are we in favor of the forward reaction or the reverse reaction? And you can always relate back to the formula, products over reactants. So if we don't have a lot of Q, right, smaller than K, that means our products is low. We need to increase products to get to 1, right, because that's the numerator. This means it's a 1-to-1. Now, this means that the products are too high, okay? Let's say they're like 4 when they're supposed to be at 1, and the numerator is just sitting, the denominator is just sitting here confused. It's like, yo, I don't have enough. Can you give me some? So we have to move backwards. So products to reactants, reactants to products at equilibrium. Okay, this is actually a really good practice to see if you understand. Okay, homogeneous and heterogeneous equilibria. Now, one thing I want to say is homogeneous means you can only see one thing, and heterogeneous is when you can see 2 or more things, okay? And we're going to talk about colloids, but that's in a different class. Now, in heterogeneous equilibria, okay, whenever you're doing equilibrium concentration and stuff like that, you never take into account solids. Never. You could take into account gases, liquids, aqueous solutions. You will not take into account solids, right? Because they're not participating, really. They're just there. They're precipitates, they're done for. Right? They do not depend on CaCO3 or CaO, which are the 2 solids here, okay? So they don't do anything. Now, what does that do? That changes our formula just a tiny bit. So usually, our formula consists of, remember this, so CO2 plus CaO over CaCO3, okay? Remember that. But when we come here, we see that CaO and CaCO3 are solids, so we don't think about those. So we just have CO2. Now, to find the solubility concentration, the equilibrium of this, we do Kc, okay, times a constant giving the concentration of CO2, okay? I'm going to give you guys also a YouTube video as well to go look at that helped me a lot because it had a lot of practice questions and stuff like that. Now, solubility. Like dissolves like, right? Now, we're going to use the KSP formula. What does KSP stand for? This guy. Kc, right? So the concentrations times a constant concentration of this guy, of the solid, times this, equals this, sorry, right? And to get this, I hope you guys have done this in high school. We use something called an ICE table, which is initial, change, equilibrium, concentration. Okay? Now, moving on, we're going to try to do some, oh no, it doesn't have any practice questions. I'll get into one and I'll show you guys. Now, these are some standard KSP values, right, for some solid compounds, ionic compounds that you can plug in here when you find Kc to get these guys. Okay, these will be given to you. You don't need to memorize these, right? Now, moving on to the common ion effect. There's a question in a YouTube video, right? And I'm going to try to recreate the question here. But for example, you have a question asking you to find the molar solubility and the concentration of the solid and stuff like that. Always, and then you have another part of the question that says this time it was in a solution of 0.5 molarity of one of the reactants. Okay, it doesn't matter. Now, whenever, ever, there's a common ion when you're doing an ice table, it's very, for the C, instead of it being plus X or plus 3X or whatever, you're going to have to get that initial concentration of the common ion plus whatever the X is. Okay, so what does this mean? Imagine everything we've done in equilibrium, whenever you add something, something else is removed, or you go the opposite way, right? Same thing. If there is a common ion being in the solution, solubility is always decreased. Always. If a common ion is there, remember, you don't even need to do the calculation, the solubility decreases. Okay? And I'll put a link for a YouTube video that you guys can go practice that I think is really helpful. This is just showing that as you add more and more and more of the common ion, right, the molar solubility decreases. Also, to add on to this, as pH decreases, the hydrogen ions increases and solubility increases, right? The effect of pH is incredibly dramatic here. Now, why? We have this formula, okay? When F is removed, okay, the equilibrium shifts towards the products, right? And CaF2 dissolves, right? Because, like, that's just what it does, right? Le Chatelier's principle, right? And the way this is removed is not really too important, but by hydrochloric acid. Now, as this is done, okay, because we have the common ion here getting taken away, the hydrogen combines with the fluorine to weakly dissociate, right? And this decreases the concentration of F, which pushes everything to the products, okay? Due to this, okay, the hydrogen ions increase. More hydrogen ions, pH decreases because acids have a pH lower than 7 and solubility increases. So, something I want you guys to think about. We have pH, we have solubility. As pH increases, solubility decreases, right? Inversely related. And this is just to show that as the pH gets smaller and smaller and smaller and smaller, the solubility increases, right? So again, inversely proportional. This is the sign for inversely proportional that I use, right? So we have you put in something, gives you something else, and one's higher, one's lower. Right, this is another real life example. I'm not really going to get into this. I don't find like it's important. And yep, just another real life example. If you understand everything till now, then these are like, I don't know why these are here, to be honest. Something that I didn't mention that's in the seminars is the Kf of the forward reaction, okay? So the equilibrium constant of the forward reaction is equal to 1 over Kf equals 1 over K reverse. So if you ever want to find the reverse reaction, you just do switch 1 over this guy to get the reciprocal, and then that's it. Okay, it might be a quick little multiple choice question. Chromatography, we kind of talked about this in the lab. Pretty much it's the separation of mixtures. We have a retention phase, stuff like that. These are all the different types. I really doubt they're going to talk about anything like this except maybe what is it. Because we did this as a lab, and I think this was just to help during the lab. It was not included in the seminars or anything like that. That's pretty much it. Now, I'm going to actually pull up the YouTube video if you guys want to watch it. And I'll show you guys which topics are important. So, solubility, equilibrium. Let me just quickly find it for you guys. This guy. Give me 1 second so I can skip the ad. Okay, so I don't know how to turn off the sound, but understand how to do this question. Okay, so this question not only shows the 0.5 sodium fluoride solution, top right over here, shows you how to get the molar solubility and stuff like that. I wouldn't watch the whole video if you watched mine, since it repeats very similar stuff for the solubility content, but just go through, for example, the molar solubility questions and see, okay, so if the molar solubility of calcium hydroxide is 6.875 times 10 to the power of -3 moles per liter, what is the KSP value, right? So calcium hydroxide, how I would do this, I'm just going to quickly do this as the last question, is this would dissociate into calcium and hydroxide, and there's 2 of the hydroxide, right? So then it gets a 2x, right? So 2x squared, then we divide it. Here, let me move this a little bit.
So it's 6.875.
So to find x, we have to do the molar ratios, right? So we do 6.875 times 2 for the hydroxide, right? And then
times 10.
As we keep going, we're going to multiply these 2 to get KSP. That's pretty much it. So it's very, very, very simple. If you know the ice tables, we know the changes. And yeah, that's pretty much it. So I hope you guys had a good time understanding chemistry. This is, again, I would really recommend looking at this video and doing the questions, trying to do them yourself. And then, yeah, so I'll see you guys on the next video. I think we're going to be talking about, thermodynamics. So yeah, bye-bye.